last section of machine learning, or people actually, in fact, normally think this is more data mining. So just to, again, recap where we are. And so roughly people think about machine learning in this six bigger categorization. And then regression is, and classification together, it's more predictive model, but it's more sample level predictive model. So we predict on each samples the targeted value or a number of targeted value that you care, and you care about the future predictions. So this group, you want to predict, you want your model to be able to forecast, to predict the future points well in terms of real value output or categorization output. So we spend the majority of the time in the classification module, and inside the classification module, we also talk about feature selections. So feature selections mostly is what those techniques we covered mostly for prediction models. So that's why I put it roughly right under classification, but you also normally use it for regression if you have too many features. And then we only leave 3 sessions for unsupervised models. And so this is more agreement actually with Professor Zhang, who's doing data mining. So in her data mining course, she covers actually much more in terms of unsupervised models. Anomaly detection, graph clustering. Here we only cover the most basic, like hierarchical clustering, k-means, Gaussian metric model. So if I have time, it's highly likely no. So I'm going to leave the expectation maximization as an extra slide that you can you should just read by yourself. So it's a very important method for audio analysis, and also you might already you should have received my emails about homework 6. So this is an optional homework, and you can get up to 5 points of extra credit. If you have time, please do finish it. It's a good homework. So we covered more kind of spread out, covered the learning theorem, especially the most important is bias and variance trade-off. So this is the fundamental of almost whenever you think or consider what algorithm fits your type of application and why one method works better than the other method. So the bias variance trade-off is very fundamental. And if you have something actually learned very solid from this course, I hope it's bias and variance trade-off. And also those discussions of comparing different approach, especially in the predictive setting, bias and variance trade-off. Complex model versus simple model. How do you how do you figure out it's underfitting? How do you figure out it's overfitting? And those techniques we try to let you implement in the homework actually are very, very good sanity tools to figure out when is my current learning overfitting or is my current learning overfitting. Yeah, so that's the most important part I really hope you get from this course. And the last 2 sections, graphical models and reinforcement learning, we don't have chance to touch. But I got a little bit for the graphical model, which is the naive Bayes classifier, which is almost the simplest graphical model, which you have y variable as parent, all the other feature variables as children. That's the simplest graphical model. But of course, there are many, many more other type of graphical models, and there's a lot of important algorithm, important theorems behind. Graphical model is a relatively math-dense group of machine learning models. And then there's another, something really hot now is the reinforcement learning. So this now, it's not just predict a sample, not just treating the samples as IID, right? So everything we cover so far, we assume our samples are independent and identically distributed. So even though I don't see this very explicitly when we introduce the method, but everything we have covered so far has this IID assumptions about the samples. So in the end, when you predict a like sample X, and then versus this predict a sample Z, and they really don't influence each other, or they don't dependent on each other. But in the reinforcement learning, this IID assumption is actually completely, this assumption doesn't hold anymore. And also there's an environment, there's a sequential dependency among the samples. So this is a very big thing to move beyond what we learned about IID cases of the algorithm prediction models, goes to not IID anymore. You have distribution shift, which is the fundamental reasons why the previous models don't not necessarily work well on the reinforcement setting. So, but we don't have time to cover that. So this course it's actually very basic. So it's a basic machine learning. So if you're interested in the other topics, this is I think this course served a good foundation, especially in terms of mathematical derivations, why these basic formulations. So it should help you a lot when you move to a more complex model of complex settings, like in this case, reinforcement setting. So all right, so this is the summary of where we are, and now let's cover unsupervised models. And then also in unsupervised models, I just have to skip the dimension reduction that session. So the specific one I skipped is PCA, but there are actually a lot of other type of dimension reduction method like CCA, the VAE, like variational autoencoder, decoder. There's a lot of in that category, but we just don't have time to cover that. But feel free to check out that basic slide, and also that serves a very good foundation of more advanced, more state-of-the-art method. Okay, so what is unsupervised model? So just roughly speaking, the unsupervised model don't assume there's a target variable as labels. So this is just a matrix of feature and sample column versus a sample row as row and feature as columns. And this is what you have. And you want to learn and mine patterns from this data. So we learn from this unlabeled or unannotated data, and we don't have a goal. We don't have a clear target variable to predict. So this is not predictive formulation, and the goal is more pattern. So I want to learn the pattern. And then there are many different kinds of unsupervised method. Specifically, or the most dominating is about the task called clustering. And in terms of clustering, it's really just I try to group, and there's nothing fancier at all. Here is I'm trying to group samples. So and then naturally there's a few questions is so are there some groups in my current data, and what defines a group, and how many groups here, and how do you identify the groups? So for this one, in fact, I mean, your eyes will naturally tell you there are roughly 2 groups, right? I mean, if you think about it, this natural thinking of 2 groups, it's based on what? Actually density, right? So just those points locate more close to each other, and these groups locate more close to each other. And these 2 groups, the points kind of separated apart from each other. All right, so very heuristic kind of definition is we want to group our data points that data points in the group are more similar or more related to each other compared to those points not in the group. And then we also want to separate our data point to make different group of points are not related or unrelated to each other. So you can think about the more from mathematical thinking is we want to maximize within group similarity, and we want to minimize between group similarity. That's just about it. Okay, so yeah, you can think about the intra-cluster distance and minimize, which is the same way to say maximize the within group similarity. Or inter-cluster distance are maximized, which is the same way to say we want to minimize the between cluster similarity. So always there's this similarity view or the distance view, which essentially just equals two sides. Okay, so what is a cluster? So again, I already said, high intra-class similarity, low inter-class similarity, and this is the most common task for unsupervised learning. But there are some other tasks like dimension reduction, which we don't cover. So this is almost the most heuristic task people start to handle data. So can I categorize my document according to topics? Can I identify like maybe proteins have similar functions? Can I group individual persons according to their political views? So this is pretty easy, but it's the most commonly used. And if you think about this, is also matches of how human organize knowledge, right? Human organize knowledge according to groups. And this kind of structure is part of how we represent knowledge. So yeah, there's another example, like you can group the languages according to their morphological stream patterns. So this is morphology-wise more similar. The root tokens are almost the same, and the difference is just prefix and suffix. So there are a lot of this type of language grouping and our species grouping, right? It's a famous evolution tree, and why we are more similar to maybe the gibbons or there's a lot of we are human are more similar to monkeys compared to human to fish, and there's a reason there, right? Because we are mammals in terms of how we passed. There's a lot of other similarities. The people also use this idea to cluster the web page search, like in this case, like Jaguar, and it can means a mammal. It can also means a car brand. And then it's naturally in the ranking retrieval, if you group the two, they are actually two different things, according to the meaning of the words. And then the other type is the Yahoo Finance or Yahoo Pages. Yahoo Pages traditionally is a very dominating organization of the whole internet web pages, and the whole categorization was manually viewed. So that was before, but now it's dominated by Google through automatic grouping. All right, so what are the major questions for clustering? So the first question is, what do you even mean as a group? And the second question is, what do you even mean one object is similar to the other object? So definition of distance measure or similarities. And then the third is, how do you represent each samples? And then how many clusters? Is it fixed number of clusters, or it should automatically be found by the data itself, decided by the data itself? And so roughly, the clustering method can be, they fall into two bigger groups, the partition-based method or the hierarchical based method. So, and also the last thing is, how do you even know my current clustering result is good? So my current cluster reaches a certain good solution. How do you tell? And how many clusters to look for? Why is that a good number? Okay, so now let's start to define what do you mean a group. So in fact, the clustering is a very subjective action. And so this page maybe it's a little bit too informal, but it gives the point is, so you can cluster all those cartoon figures according to their roles, that they're a part of the family or they're part of the school employees. You can also partition those cartoon figures according to gender. And it's really difficult to see, and this group is better than that group, right? It really depends on what you care. And what do I care the most? And then the next one is even more, like a better figure. So I'm trying to cluster those cubes. I mean, how do you even define, is this a better cube compared to this cube? This is grouping. So the left side groups the cubes according to color. The right side groups according to the label, the number, the letter on the cube. Is this a better clustering than the left is better than the right? No, actually you really don't know, right? It all depends on what you care more. And then even more is the next picture, which is kind of funny, but so we see the girl is kind of looks similar to this puppy. And then why? I mean, intuitively you actually know because their hair looks pretty similar, the hairstyle. But in the end, clustering is a very philosophical question. And like we said before, how to cluster samples, it's not entirely a mathematical task. It's a philosophical question. It's about the specific data, about specific applications. What do you care the most? So, this is not task agnostic, right? Whatever we said, I mean, it depends on you, right? It also depends on the user. So maybe this user cares about hairstyle more, the other user cares about species differences more, and there's no way you cluster this as similar. So it depends on the end user. But as a method, we just carry a more pragmatic approach is, okay, so let's just assume all the samples can be represented in a vector space. And that's more a numerical vector space. When you're facing this numerical space and you actually do not know what feature is more important than the other, in that type of situation, what would you do, right? Okay, and then let's just use simple metric-based similarity definitions to define similarity about samples. So everything after is about just, let's assume we don't know anything about what the user care, assuming you're given this vector space representation. What do you do? It's more a blind, black box type of clustering, just to tell you, okay? But remember that this is not the best that you can do, or you should do, because clustering is a very subjective task. All right, question here, maybe. Yeah. Always, whenever performing clustering, be careful. Don't make too conclusive conclusions because the clustering itself, it's very subjective. All right, okay. So now, because we don't assume anything, we assume features are equally important, and then that's in a vector space, then we just use normally defined distance metrics to measure the similarity among points, among samples. So what makes a good distance measure good, right? So normally we want to look for those, the four properties. The property like symmetry, property of self-similarity, property of positive separation, and the properties of triangular inequality. So let's see, why do we care that? So symmetry means AB the distance among AB is the same as distance as BA. So because you want to avoid, you can claim Alex, it's like Bob, but Bob looks nothing like Alex. So we want to have those kind of metrics or distance measure have symmetry properties. And the second property is called self-similarity, which means if you do the distance measure of A sample versus itself, it gives distance 0. And this is an important property is, so if this doesn't hold, it's you may have, Alex looks more like Bob than Bob itself, which is odd, right, if you think about it from the common sense, right? So everything here, in the end, trying to make or try to enforce the common sense properties on the distance measure you create. So if you think about it, you have a lot of domain related maybe distance measure, and then if you want to have the generic clustering applied on it, so better check if they follow this 4 type of properties, because this gives you good common sense guarantee in terms of what type of clustering you get. Okay, so then positive separation, if A and B, so AB equals to 0, distance equals to 0, if and only if A equals to B. Because we want to avoid if you get distance maybe C and D equal to 0, but C and D are not the same. Which means what? Which means using this distance measure, there's no way you tell apart C and D. And there's no way. And then triangular inequality, we always know that, right? This is give a good geometrical properties. So Alex is more like Bob, and Alex is very like Carl. And then you hope this triangular, this is like 2-step relationship could give you a property, and because A and C, distance of A and C and distance of B and C, so they're all very similar to C, A and B. So you want distance of A and B to be smaller than the summation of A and C and B and C to just guarantee the A and B are not too different from each other, just because both are very similar to A and C. And this is again is a common sense, right? This is a common sense property. And you just use mathematical formulations to try to check if my distance measure satisfies that common sense property. So in the end, you can define whatever distance measure you like, right? But having this kind of property could guarantee good properties of the classes that you use clustering algorithm to generate. Again, so then let's give examples of the distance measures satisfy that 4 property. So normally, and in fact, so they all follows what we learned before, the L1, L2, Linf. So this is the Euclidean distance is the L2 norm, which is just each element, the differences take quadratic and then sum over all the elements and take a square root. That's your Euclidean distance, right? Then the L1 distance, then the Linf distance, they are all under this family called Minkowski metric family. And then just to give you a geometrical view, and then the x and y, the Euclidean distance is geometrically just the line connect x and y, and that's the length of that line is the Euclidean distance. And then the L1 distance is just 3 plus 4, and then L sup distance is just whatever is larger. In this case, 4 is larger. So it's all very intuitive. It's really just this triangles, the right angles, longer corner length, or the direct connected length. So they all follow that 4 properties. And the classic string distance called Hamming distance, which we already normally learn from our algorithm class, is in fact a something called Manhattan distance. It's actually the L1 if your features are binary or symbolic. And then there's another classic distance measure called Pearson correlation, which we covered many times before when we talk about correlation among in the feature selection section and also in the Gaussian mixture model. So we had a lot of discussion about Pearson correlation. It's a bounded measure. It's from +1. It's from -1 to +1. It's a unit. It's actually not unit dependent, and also the famous cosine distance is a special case of Pearson correlation. Cosine distance measure is really just the Pearson correlation on centered data. So there's no mean x, mean y, x, y if there are zero vectors, and this is in fact just cosine distance. And also there's good reason why they're good, right? So correlation, Pearson correlation is unit independent, which means it's very well used in especially time series analysis to capture two time series. Are they correlated with each other? What are the distance among two time series data? So in this case, if this gene B or this whatever is time series got pushed up in the unit, because when you measure, there's some maybe has on the different scales, and it's pushed up maybe 10 times more on every entries, but the Pearson correlation you calculated with the B and versus the A will be still the same because the properties of Pearson correlation. What it really measures is just if X improves, what's the tendency of also B improve. So it's a good measure because of unit independence property. All right, so this is just pretty popular distance metrics, L2, L1, Linf, and Pearson correlation. And yeah, so but it depends on the domain. Different domain has different domain-specific measures, so we're not going to cover. So now let's talk about clustering method. All right, so clustering method can be just roughly categorized into two groups. The first group called partitional method. So usually you start with a random partitioning, and then you refine that partition iteratively. The most classic approach called k-means. And then more advanced on extending the k-means is the Gaussian mixture model. Then people further extended into more generic mixture model-based clustering. So we're going to cover is only k-means and Gaussian mixture model. And then the other type is called hierarchical clustering method. So it's really just building a binary tree. It's use a binary, it organize all the samples inside your current data using a binary tree. So normally we call this called a dendrogram structure. You're learning the dendrogram to organize your samples. This dendrogram can be learned from bottom up or from top down. So there are different variations of the algorithms. So let's start to see a hierarchical algorithm. So in the end, again, so like we said, so it's very hard to see why we're doing this way. So why we are partitioning our samples into groups, why we are partitioning or we are organizing our knowledge into a hierarchical, more like a tree structure. So, in the end, just if you think about data mining or a pattern, organizing the data, the goal is what? The goal is to improve how human organize the knowledge. And if you think about your brain has chunks, right? Human brain has different chunks. And your brain naturally organize the memory, organize knowledge into chunks. And there's also a hierarchical structure inside how brain organizes the signals coming into our brain. And everything of all those algorithms you can think about, we're imitating how human organize the knowledge. And the hierarchical structure is a very strong, it provides a very strong structure onto the knowledge. And this knowledge matches how human organize their knowledge in mind. So so this is why hierarchical structure is so dominantly used in almost every scientific discipline, right? People organize, think about species, think about web pages, think about everything, astronomy, physics, and all this has this hierarchical view to organize knowledge, organize a discipline. So, how do you create a hierarchy if you do not know the hierarchy beforehand? So normally in the different science, you have experts, you have professional researchers build the hierarchy of the knowledge of the discipline, right? But when you have unknown data, you don't know anything. How do you get a hierarchical structure to organize the samples? So this is about hierarchical clustering. So the question is in the end, so you want to find the tree structure to organize your data points, right? And if you think about it, this is a search task. I'm searching a tree to organize my data points. And then the most brutal force method is, okay, so if my goal as the general clustering goal is maximize inter-cluster similarity and minimize the intra-cluster similarity, then I'm using this as my loss function, right? So everything we did before in the predictive model setting is there's a loss function. And you can use it as a loss function. And then my goal is to look for a model. What is my model? My model is the tree, that the tree represents my data. So then the whole task is, for whatever given data, I want to look for a best tree, maximize the intra-cluster similarity, minimize the inter-cluster similarity. But however, this is an extremely difficult task. Let's just see the numbers. So if you have number of leaves, like 2 leaves, the number of possible tree, this dendrogram is a binary tree. It's 1. If you have 3 data points, the number of binary trees to organize 3 points is 3. If you have 4, that's 15. If you have 5, that's 105. And then if you have 10, there are 34 million possible binary trees actually to organize the data points. So there's no way you do brute force type of scoring. Just do global search, the optimal model that fit my data according to the loss function. So because of this is it's not polynomial. There's no way using polynomial method because the search space is certainly not polynomial, right? It's a very, very it's actually extremely non-polynomial search space. So again, so that's why people use this very, very greedy local method to build the tree. Question about this? Yeah, so extremely difficult target space because my target is a tree, right? I'm trying to identify a tree to fit my data, then according to a scoring function. All right. So it's actually, again, using a funny cartoon example is, so normally hierarchical clustering, it starts from either a similarity matrix or a flip side is distance matrix. So you can think about this case is, you can just get a distance matrix to capture. So this small cartoon versus this with the blue hair, the distance is 2, and the smaller cartoon figure versus this purple hair. The distance is 4. And then you just start from this matrix, distance matrix. You try to find the best pair. You try to find the best pair that is capture the smallest distance ever. If you build a cluster, maximize or minimize the within cluster distance. Again, I'm building a small cluster, minimize the possible distance within the cluster. Which is, if you think about in the first step, I'm trying to find a 2-person cluster, which has the smallest value of distance measure, which give me the best cluster ever for my current state. And then you compare all the numbers here, and because this is 1, and that's why you cluster this 2 to build up the first cluster. So again, my goal is minimize the within cluster distance, maximize the between cluster distance. In this case, because it's a hierarchical structure, let's just focus on minimize the within cluster distance. So this is my goal, my loss function. So then you just, because there are totally 1, 2, 3, 4, 5. There are 5 figures. Building a 2 cluster, how many choices? 5 figures, pairwise clusters. This is the simplest combinatorial ever. And also be careful about the 0 here. Remember the distance measure we said, a good distance metric should have cell similarity property. So A is always the most similar to A. B is always the most similar to B. Alright, so you just compare all the possible pairwise combinations, and then you pick the one give you the smallest, which is 1, which is also both purple hair, and then red dress versus the blue dress, and they are the first cluster. Okay, so you got the best, and then this is your current cluster, and then you're trying to figure out the next best cluster, because that's all you can do to make it feasible to look for the binary tree, right? Next best cluster from this figure is from this matrix is 2, and this is the smallest number, 2. And then this is how you group this 2 together, you group the other 2 together. And then what do? You already have 2 cluster, and then you further trying to find, for my current situation, the best cluster ever. But then there's a situation, I'm going to talk about how do you group these 2 together. So rather than, you have only this teacher left, and then why don't you just group the teacher with one of the cluster instead of group the 2 cluster together? So what type of metric you use? So it's about how to compute the distance between clusters, because when you have the middle level clustering results, the distance calculation is not just among samples anymore. It's also among the clusters or a specific sample with a certain cluster. So then this gives the differences of variation of bottom-up hierarchical clustering. So how do you calculate distance among clusters? There are 3 different rough kinds. The first kind called single link hierarchical clustering. So when you have 2 clusters, you try to calculate the cluster versus cluster distance measure. What you use is the nearest neighbor members inside each cluster. You use the smallest distance that's possible to represent the cluster, the 2 clusters distance. Or there's the entirely the opposite called complete link method, is you use their furthest members, the distance measure, as the cluster distance measure, or you use the average. So let's see concretely. So if you see this class C1 and class C2, how do you measure, because each one of them have multiple members, right? How do you measure this cluster versus this cluster's distance? And the single link is, I'm using the two members inside each. This specific line represents the closest member distance. I'm using that closest member distance as the distance among the two clusters. And if you're using this single link using the closest member, so clearly C1 and C2 should be grouped together first, because this specific length is smaller than C2 or C3. So yeah, this is a single link, and then you can actually tell this creates some kind of pretty thin and slim stretch out clusters, and then it may potentially generate long and skinny clusters. And then you can also use the two members that is furthest apart in the two clusters. In this case, is C1 and C2. This is their current complete link distance, that distance length line, and then C2 and C3 is in fact actually this, that's the furthest line. When you compare, so if you use complete link, and then C3 and C2 are more closer to each other versus C1 and C3, and also versus C1 and C2, and also versus C1 and C3. So this actually potentially give you a more tighter cluster, because you try to, this in fact trying to push trying to push more closely related clusters more together. And the previous one allows, as long as they have some touching, they are close together in some points, not every point, right? So, but this requires they are close to the two clusters are together almost among all the points. So that's why this more creates you more tighter, more more tighter, bigger, tighter clusters. And then the third is just you calculate all the possible pairwise, and then you use the average. Okay, so I want to do a computational complexity analysis now. Because I think it's the most interesting, because all those methods, all those clustering methods are very, very heuristic driven. And they're mostly greedy, mostly local. Then what really matters is, in the end, it's more computational cost, right? Is it fast? How fast? What's the computational, maybe a memory cost or the time cost? So let's see in this case. So we already said, right, to have a, okay, let me maybe check you, have you understand the hierarchical clustering, because such an easy algorithm. So this is a given distance matrix, and this is the points 1, 2, 3, 4, 5. The index here matches that matrix index. So who and what is the first cluster? Who and who should be first clustered together? Okay, there's a little bit, sorry, this is 1, this is 2, it's, yeah. It's not entirely, yeah, it is a shift. Yeah, so look at this, yeah. So, again, this is a good distance metric. It satisfies symmetry property, right? Because it satisfies the symmetry property, I only need to just show you the lower triangular, because the upper triangular equals to the lower triangular. First is symmetry distance measure. The second property, common sense property, is all these diagonal elements are 0. They are similar. And then I can just see the smallest possible numbers in this matrix is 2, So, which means I should just cluster 1, 2 together. Okay, so what's next? After I cluster 1, 2 together, what should be the next?
2 and 3.
Alright, so if I cluster the 1, 2 together, the first step, what should I do? I actually should revise my matrix, right? Because now, what should my matrix look like now? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Alright, so the 3, 4, 5, if I'm copying, what should I do next now? Because I should actually calculate all the possible pairwise distance to create this distance matrix among all the possible cluster, right? So let's see. 1, 2 versus, so first of all, let me put all the 0 there. So 0, and it's a bad matrix writing. And 0, okay, so, and because 4, so this is like 3, 4, 5, and those are not revised at all, right? From the original matrix, I can just copy. So I can copy, what should I copy here? 3, 4, 5, 7, 5, oh no, that's not right. It is 4 and 3, right? Who is 4 and 3? 4 and 3, that's 7. Did I write something wrong here? 1, 2, 7. This is 4, right? 4 and 5. Yes, that's correct. And then 3 and 5. 3 and 5 is, so this is 7 and 5. And then what is 1, 2 versus 3, 4, 5? 1, 2 versus 3, 4, 5. 1, 2 versus 3, what is it? So we're using a single link. 1, 2 versus 3. 1, 2 versus 3 is supposed to be 1, 2. So all the 1 and 2 versus 3, 6 and 3, right? Single link means what? The smaller number. So that's why I should put 3 there, right? Should I put 3 there? Now 1, 2 versus 4. What is 1, 2 versus 4? 10 versus 9. I should put the smaller number there, right? So this is 9. And then 1, 2 versus 5. 9 versus 8. I should put 8 there. Okay, so, and then what's the next cluster? 1, 2 versus 3. Yeah. If I don't generate this matrix, if I directly just see what's the next in the original matrix, and that should give me, I don't even know how to generate that. 2 and 3. Yeah, because 1 and 2 are already clustered, right? So you can't just use the second minimal points from the original matrix as the next created choice. You have to regenerate the matrix and to be able to know what is the next. So this is the process of performing hierarchical clustering. Okay, so because I'm doing this process to you, right? And now let's do the calculations. So, you have all the points. Each point belongs to, this is on data points, right? Each data point is a p-dimensional vector. And this means if I'm calculating Euclidean distance or whatever Minkowski distance, what's the cost to calculate maybe a distance among xi and xj? Time cost. Just for one pairwise distance measure. For one pairwise distance calculation, what's the asymptotic number I should put it there? If you remember what I wrote before, Minkowski distance measure, it's all the way back. Okay? Yes, Minkowski. So let's just say Euclidean distance. How many operations here? If on a p-dimensional vector. How many operations here? It's actually OP, right? So there are P element-wise subtraction quadratic operation, and then you do a summation, because that summation is O1 cost, and then square root is also O1 cost. So that's why I'm writing the time cost of calculating either the Euclidean distance or all the other Minkowski distance is similar. They're element-wise operation. They're totally p elements because it's p-dimensional, right? So to calculate this needs a cost of time cost in terms of flops, or yeah, that's just same time. It's OP. All right, so then create this matrix. What is the cost? It's all like matrix, all the possible pairwise matrix. What is the cost here? To calculate all the possible pairwise Minkowski maybe distance measure. How many elements here? Let's assume there are a total of n elements, n data points. x1, x2, down to xn. Total n points. It's same as our matrix, right? N times p. Here, there's total of n points. And then this means your pairwise distance matrix is a n times n matrix. And then that means creating this pairwise matrix needs time cost of n quadratic p. All right. Okay. So this is only the first step. Now, I need to get the smallest number as the current stage clustering. Smallest, this is actually own cost. That's just smallest, actually O(n) quadratic, because it's smallest. It's a loop over all the possible n quadratic. It's O(n) quadratic. Yeah, so you got the smallest cluster, then you need to recalculate the matrix. So what is that matrix cost? I already did to you, right? Roughly. So there's a best operation. You've got the best current cluster. This cost about O(n) quadratic. And now I'm readjusting that distance matrix, right? So what's the readjusting the distance matrix time cost? So in fact, if you think about it, it depends on the size of the current new cluster from the previous cluster. So the current stage versus the previous stage, right? It depends. It depends on, is this a sample? Is this a cluster? But let's just assume for the specific setting is I need to recalculate the size of the cluster. In that size of cluster, I'm performing the mean operation. So you have to just then recalculate the specific cluster's distance versus all the other clusters. And the number of cluster is upper bounded by n, which means the next recalculation is On, I think it's On cost. This is On, and then depends on the size of the cluster. So, okay, and it's a little bit, okay, so I'm now, the first stage is the distance matrix, right? The second stage is to calculate the new cluster versus all the rest. The versus all the rest, the number of the rest is upper bounded by On. And the size of this is also upper bounded by On, which makes the recalculation of this new matrix is upper bounded by On quadratic. I hope you get it. Yeah, but that's okay if you don't get it. So, and this actually is upper bounded by On quadratic. Let me normalize. It's all capital N in this. I write it capital N. So, and then you have to do this iteratively. If you do badly, you need to perform a really. So, how many is this iterative recalculating matrix, then reassigning cluster? How many times you do this? How many times you do this? Actually, it's upper bounded by N2. Because this is a hierarchical clustering, right? Which makes what? So I actually skipped all the details, and you have to read matrix again, until every point is part of a cluster. So I think I have a computation. Yeah, let me move to that page. So if you do naively that best matrix, figure out the best cluster. If you do naively, this is an n cubed time cost algorithm. So this is the reason why I'm doing this, but yeah, try to figure that out. But so in the end, but you can do a little bit smarter, which gives you an algorithm is n quadratic log n. You can do a little bit better, but naively it's n cubed cost. So this gives you an example of a single linkage. It normally gives you very, very thin, very, very slim cluster, and this gives you a little bit more balanced because it's calculated the average distance among clusters. The height itself represents the distance between the objects and cluster, which is a really good thing. You can actually use the height to represent it. So the cluster itself captures a lot of knowledge. Yeah. So what we just covered is only a bottom-up approach. So you start from each sample, each object in different separate cluster. You repeatedly grow the cluster, and according to the algorithm, and you join the closest pair of clusters, and until there's only one cluster, summarize all the data. And the history of merging itself forms a binary tree, and we normally call that dendrogram. And the top-down, there's another approach, is top-down divisive, which we are not going to cover. Yeah. So the computational cost is, in the first iteration, it's need to compute the similarity measures, which I already covered. It's On quadratic P cost. And then in each of the subsequent, there's actually n-2 merging iterations. You can calculate it because the first is 2, and then if you keep adding a cluster or so you can actually calculate this a total of n-2 merging operations. So that's the reason why, and in the previous calculation I give to you here. Actually here, yes. So the size of the cluster is upper bounded by On. So I'm just assuming the worst possible cases. So every time you're adding a node into my current cluster, that's the simplest way to calculate cost, right? Every time I'm adding one here, which means I need to calculate all the rest of the non-cluster points versus my current cluster, and that distance measure calculation is upper bound by open quadratic, and the size of the nodes left not in the cluster yet is O(n), and yeah, so that's the reason why the naive method gives you NQ cost. All right, so yeah, so feel free to do this again, and then you get the final cluster look like this. And you can also change to complete link or average link, and that will give you a different type of clustering. And I think that's everything I want to cover. So to summarize about hierarchical clustering, a good thing is you don't need to specify how many clusters because it automatically gives you a tree to organize the data. And it might map very nicely to human intuition. This is how humans organize their knowledge in their brain. And they don't scale well. There's an issue is the time complexity is actually at least O(n) quadratic. It doesn't work for when your n is large. And like any other heuristic search, and you're doing greedy local at every stage. I mean, is the final binary tree the best tree? You actually don't know because you don't even search that way, right? You only perform greedy at every step of clustering. And the interpretation is very nice because the height, the order of how the cluster are grouped together, it's all part of the properties of your data. So this is why actually hierarchical clustering is used very dominantly in many different scientific disciplines, even though this is such a simple method. All right, so to summarize, clustering, and this is about grouping points, and then the choices is, in the end, it's a representation is what type of distance measure you pick. And we should have good distance metrics follows the 4 properties we had because that's really common sense property. And there's no clear defined loss. In fact, in hierarchical clustering, I just showed you a very intuitive loss function, which is to minimize the within cluster distance. But there's no formally defined the loss formulation. It's performing the greedy local bottom up or top down. The model itself is a binary tree. We normally call that a dendrogram in this setting. So I think that's